Yes, Sanidhi, Neha, am I audible to both of you?
Yes, ma'am.
All right. So, good evening, class. See, Sanidhi, in this batch, we are one more class ahead of what is done in your batch. Okay. So, one thing we can do is notes are already ready because I discussed this here earlier. I think you were facing trouble with the timings, no, Sanidhi?
Yes, ma'am.
Okay. Why exactly? Because of school?
Yes, ma'am, because of school.
Okay. So it's just that it's just one class difference. So I'll provide you the video lecture also today. Okay, that you watch. And apart from that, I'll discuss the things before starting. Neha, it would be a revision also for you. Just few minutes it will take because this she is lagging by one class. We have just discussed. And I'll start with whatever I did yesterday because Neha, you were absent yesterday. So Sanidhi will catch up from there. Sanidhi, in your batch, we discussed that two types of the work done we have discussed that when force is constant, then you have the formula is Fs cos theta. Okay, and when the work done is force is variable, you use the formula integral of F dot dx. And till these two questions we did in the class. Remember, Sanidhi?
Yes, ma'am.
Okay. Now, the next question and all. So from here, it was already covered in this batch. So in your regular class, that recorded lecture or basically the recorded lecture of last class, which is missing, that I'll share, but let me discuss it so that when you watch, you don't have any trouble. And for the notes also, you can just take the screenshots and leave some pages for meanwhile. Okay.
Yeah,
See,
ma'am.
force is given as 3x square plus 2x. Now, this is a variable force because it is depending on x. If I put the value of x as 0, I'll get the force as 0. If I put the value of x as 1, I'll get the value of force as 5. So like this can be, it will increase and it will keep on changing. That's why we say this is a variable force. So you basically integrate it from 0 to 2, you get the answer. If there's any difficulty with integration, please let me know. I'll help you with that. Now,
Okay.
talking about a small topic, graphs. See, we discussed this earlier also when we did motion in a straight line. If two quantities are getting divided, the third quantity is given by the slope of the graph. Like if I have distance getting divided by time, if I say x divided by t, so my third quantity is velocity. So the curve basically that will be given by the third quantity, which is velocity, will be given by the slope of the graph, okay, which is equal to tan theta. We have already discussed this. But if two things are getting multiplied, like if I multiply velocity into time, that will give me the displacement. So now it won't be given by slope tan theta, it will be given by the area under the curve. Now out of these two, work done is force multiplied to displacement. So you use the area under the curve. Basically the work done is given by the area under the curve. So whatever area is above the displacement axis, it is taken positive, and below is taken negative because force and displacement both are vectors. Your work done is scalar or work done is just a scalar quantity, but force and displacement both are vectors. So that's why we calculate the area under the curve. We don't take tan theta in this case. Whatever figure is made, you calculate. Like if this is the figure, you see two figures are made here. This is first figure, this is second figure. Now look, this is the rectangle, this is a right angled triangle. So for the rectangle, area is 2 into 3. For the triangle, the area is half into base into height. That is 4. Now, since this is below the principal axis and this is minus 2, you'll have to subtract them. 6 minus 2, 4 joules. So what you can do, you can write them separately and then subtract, or you can add them, and whatever quantity is negative, whichever is negative, just put it so that eventually you get the correct answer, similar answer. That's how we use the graph. Sanidhi, this part is clear to you?
Yeah, ma'am.
Okay. So, do you want to take the screenshots now or you want to see it through the video? How would you prefer?
I'll do it through the video.
Okay, through the video. All right. So you make the notes from there only. Okay, forwards. Yeah.
Okay.
I'm just briefing you so that you are able to connect with today's class. Now, when this that portion completes with work, and in your batch also, the class which we had before, the topic work done is also done. Now we are on energy. Here also we are on energy. So energies are of two types. Energies are of various types, but you just have to do two kinds of energies: the kinetic energy and the potential energy. Now, kinetic energy is related to temperature as well as it is related to movement, temperature and movement. While potential energy, this is related to forces. Forces should be there. And when you have kinetic energy and potential energy combined together, it can happen they are solely existing. Only kinetic energy is there, only potential energy is there. Or it can happen that both of them are present. Kinetic is also present, potential is also present. So basically, kinetic plus this potential gives the mechanical energy. Combined, we call it as the mechanical energy. And this mechanical energy is used in the mechanics, the kinematics, and the entire mechanics. First book is your mechanics. So we started with kinetic energy and we were still on kinetic energy. So let me just brief you what is this. Basically, you have to know kinetic energy is given by the movement whenever motion of the body is there, because its formula is very simple: half mv square. This is the formula of it. Half mass into velocity. So, mass is a scalar quantity, but velocity is related to movement again. So, if velocity is related to movement again, that means when the body moves, then only kinetic energy will come. If I say somehow velocity is zero, then my kinetic energy will also be zero. So, kinetic energy is the energy possessed by the body due to its motion. It's called the kinetic energy. Okay, whenever it is related to movement or motion, that is known as the kinetic energy. You just have to see if is the body moving or not, is the body in motion. Whatever you've studied in the kinematics part, that will be repeated. So this is the simple way to analyze kinetic energy, and kinetic energy is easier in comparison to potential energy. I'll discuss potential energy if possible in today's class, then we'll be able to understand this. Now, there's a concept of work energy theorem. Work energy theorem basically says that whatever is the work done is equal to the change in kinetic energy. Whatever is the change in kinetic energy, this work done is equal to the change in kinetic energy. Now, when we say change means final kinetic energy minus the initial kinetic energy. This is known as the change. So you need to calculate the final minus initial, whatever kinetic energy you are getting, whatever is this change equal to. So we say this is the work done. Basically, see what happens is different energies are present in our system, different kinds of work done we obtain. The whole concept of work done and energy and power, all these basically heat energy, not power exactly, but the different kinds of energies that we have, more or less all the kinds of energies are just converted from one form to another. Like kinetic is converted to potential can be converted to internal energy. Like this, various energies are converted. Mechanical energy is converted to electrical energy. Lots of energies are just converted into one from one form to another. That's why there's a very famous sentence in science that we study in our lower classes: energy can neither be created nor be destroyed. So it can neither be created, means you cannot add it somewhere, nor be destroyed, means there is no possibility of destruction. Okay, what is happening is if there is a wasteful energy like friction and all, then that will be dissipation, means it will turn into heat energy, but it will convert into some energy. You cannot just eliminate some energy from the total system. So work energy theorem basically says that work done is equal to change in kinetic energy. Am I clear, Sanidhi?
Yeah, ma'am.
Oh. Now, for this, often a question comes to prove it. Prove that work done is equal to change in kinetic energy, or write the statement of work energy theorem, derive it. So derivation is very simple. Initial mass is there, initial velocity is v1, a force has been applied and the body moves to certain velocity v2. We know force is equal to ma, we put that. We also know acceleration is dv over dt, so we put it. M dv by dt, see this is mass, this is acceleration. Ma dx. Now dx over dt from this side is nothing but velocity. Velocity is dx over dt eventually. So when you replace it, you get m dv dv. You also have to change the limits because here x was getting differentiated, so you use x1 and x2. Here velocity is getting differentiated, so you have to use v1 and v2. When you integrate, you get mv square by 2. Put the upper limit, lower limit, you will get mv square minus v2 square minus v1 square by 2. You separate the terms. Final kinetic energy minus initial kinetic energy is the change in kinetic energy. So this is basically what the theorem is. One more concept and then we'll begin, Neha. I hope you're there, Neha.
Yes, ma'am.
Okay. Momentum and kinetic energy. See, momentum, Sanidhi, can you tell me its formula? Momentum of the body. P is equal to mass into velocity. Okay, this is its formula. Now see,
Okay.
P is equal to mv. Now kinetic energy is half mv square. Okay, so when you multiply and divide it by the mass, you get half m square v square by m. Now, if momentum P is mv, so its square will be just the square of this term, this square, this square, this square. That is P square, m square, v square. It means this m square, v square, m square, v square is nothing but P square. Half mv square was there, right? We just divided and multiplied it by m. So that gave us m square, v square, which is nothing but square of momentum. Got this point?
Yes, ma'am.
So the formula of kinetic energy and momentum, this is a basically relationship between kinetic energy and momentum. That is half p square by m or p square by 2m. Now the question was the percentage change in momentum is given as 10%. It is percentage change in kinetic energy. So this is a basic percent question, just in case if you've forgotten, because in the batch, in your batch, your classmates had a lot of difficulty with this percentage. See, whenever you calculate percentage, remember this, look at this. Whenever there is a percentage increase, okay, this is for the percentage increase. The new quantity is given by the original plus whatever is the percentage increase given. And if it's a decrease in percentage, then the new quantity is given by original minus the percentage in the original. So this is what we have already studied from the lower classes. It's just that this is not in very use to us, so we forget it. So this is there from your lower classes itself in your maths, but it will be used, and most of the questions come from percentages also. So initial momentum, let's say, is P. Now final momentum, the new momentum will be P plus 10% of P. Original plus 10% of P. So P plus 10 by 100 into P, because percentages, when you have to convert it into fraction, you divide by 100, and when you have to convert fraction into percentage, you multiply by 100. If I have 5, when I say it's percentage, we'll have to multiply it with 100. Initial kinetic energy will be, initial momentum is P, so P square by 2m. Final momentum is 1.1 P. So square it, it will become 1.1 P square, 1.1 square P square by 2m. That is 1.21 P square by 2m. Now percentage is always given as change in the quantity by the initial. Means change in the quantity means the final kinetic energy minus the initial kinetic energy. So final minus initial by initial. So from here, P square by 2m will be cancelled. You will be just left with 1.21 minus 1, that is 0.21. That is, when you multiply it with 100, it is just 21%. Did you get a gist of this, Sanidhi?
Yes, ma'am.
Okay, if there's any trouble with this question and you want me to repeat or something, please let me know. I'll just let you stay at the end of the class, or I'll ask you to stay back if time
Okay.
exceeds. Okay.
Yes, ma'am.
Now, this is a formula-based question. Mass and initial final velocities were given. Displacement was given. This you can look up in the video. You'll find it properly explained. I'll just share the video now. Let me just complete a portion, then I'll share. Change in kinetic energy was calculated, half mv final square minus half mv initial square. And work using work energy theorem, work done was calculated. Using the displacement and work done, the force was calculated. So it was a very easy question. Just have a look at it. Okay. Coming to the next topic from here, Sanidhi, you can ease up and understand. See the types of work done. There are different kinds of work done, different types of work done. Positive, negative, zero. Okay, three types of work done are there: positive, negative, and zero. See, work done is a scalar quantity. So negative work done doesn't mean you have the direction opposite or something. Negative work done just tells the angle. It is just describing the angle between the two quantities which we have, the force and the displacement. That's it. Remember, work done, this will always be scalar. So how do we have this work done as positive or negative? Positive, see, if your theta is acute, theta acute means when angle is less than 90 degrees. So this is acute. So in that case, what will happen? Theta will be positive. So work done will come out to be positive. The value will come out to be positive. That's what a positive work done is. Theta is less than 90 degrees. So this basically tells that force and displacement are at an angle less than 90 degrees. Second is negative work done. Negative work done basically means theta is obtuse. Obtuse angle means theta is more than 90 degree but less than 180 degree. That is our obtuse angle. So obtuse angle, basically theta is positive. Why? Cos we are using. Cos theta will be positive. I forgot to write cos here. Similarly, here cos theta will be negative. Okay, here cos theta will be negative. Eventually, the work done will come out to be negative. But that negative value will just indicate the direction, the angle between force and displacement. It doesn't mean that this is giving you the direction of work done, that this is situated towards this or not. Work done is scalar. It's energy. Energies are always scalar. You'll never have energy as a vector quantity. Any kind of energy. Okay, last is zero work done. Now, in zero work done, two possibilities are there. First possibility is that, can anyone tell me which angle should be there to make the work done as zero? What should be the angle to make this zero? Yes.
Can you repeat the question?
Question is, what should be the value of theta so that I get this zero? Work done is zero.
90.
Yes, 90 degree class, cos 90, 0. Okay. So if force and displacement, they are perpendicular to each other. This is the force, this is the displacement, and they are perpendicular to each other. So cos 90 degree is 0. You get the work done as 0. There is one more possibility. The second possibility is that, what if there is no displacement covered? I told you all when we discussed work done that if a person is there and this person is holding, let's say, 10 kg of heavy weight for 4 to 5 hours at a spot. He didn't move, but he is holding this such heavy weight. In literal terms, we know he has done a lot of work, he's tired and on. But in physics, we'll say no work has been done, because for physics the definition of work done is there has to be an applied force which will produce a displacement. Applied force is there but there is no displacement. So in physics, even if you're holding 10 to 15 kg weight for 5 to 10 hours without moving, without producing any displacement, any change in your position, you are not set to do a work. Okay, so here if displacement is zero, directly we'll have force into zero, that is zero. So your work done will also be zero. That's it. Okay, I think you must have found this topic easy and got it.
Yeah, ma'am.
Just write it down. Then we'll begin with the potential energy part. But before potential energy, I just have to tell you the conservative and non-conservative forces. Okay. Meanwhile, Sanidhi, I'm sharing the video with you. Okay.
Okay, ma'am. Ma'am, ma'am, you can scroll.
Sanidhi, you've also written?
Yes, ma'am.
Okay. See, talking about the conservative forces, this is a completely new concept for all of you. And this is a concept that will be staying with you in class 12th also. Because these are forces. Forces are there in every unit. Okay. You have the forces here, you'll have electrical forces in class 12th. So, conservative forces mean if I say, look, I say this is point A and this is the point B. Okay, A point is there and this is the point B. Now, if I am doing the work, let's say if I go from A to B like this is one possibility. I am going from A to B like this. Second possibility is that if I am going from A to B like this. This is the second possibility. This is the first one. This is the second one. And third is if I am going like this. So three possibilities I have given. Okay. Now, conservative forces are those forces which do not depend on how this path has been traveled, whether this is first or second or third. It doesn't depend on that. It depends just on the initial position and the final position. Okay, final point, initial point and the final point. That's it. So work done in all the cases would be the same because it doesn't depend on the path traveled, initial and final point. So work done 1 will be equal to work done 2 will be equal to work done 3. That is what is meant by conservative forces. Okay, you have these 3 points, 1, 2, 3. It just depends on the initial and the final point. Okay, so forces in which work done is independent of the path. It just depends upon the initial and the final forces, like your gravitational force, your electrostatic force, okay, your elastic force. These will repeat themselves. Okay. Now, a little revision of a concept we already did in the laws of motion, the concept of the internal force. See, if I say my system is there, means if I am studying Earth and the Sun, something I'm studying about them, and I have the Earth and the Sun. So I say my system would be the Earth plus the Sun. This is my system. Anything that is present apart from the Earth and the Sun will be counted as a surrounding. So we can say, okay, system plus the surrounding make up our entire universe. They make up the entire universe. Universe, you have the system which is under observation and the rest of the system that is present. Now, if I say there's a gravitational force existing between the Earth and the Sun, so this will be categorized as an internal force because this is a part of your system. So this is known as the internal force. And any other force which is acting from outside will be categorized as the external force. This is categorized as external force. This is categorized as internal force. Okay, internal forces, external forces. Now, when we talk about the work done, okay, that point I'll tell you later. First, just I'll repeat this again. I'll repeat it. So, if you have a work done in a closed path, means let's say this is point A, this is point B. So, closed path means body moves from A to B and body moves back from B to A. So, your initial point and final point are the same. Work done is 0. There, because it doesn't depend on the path traveled. It just depends on the initial and final point, like your displacement. Now, why are we studying this topic so urgently and why in this chapter? And the reason behind is that the potential energy which we are about to start, potential energy just depends on the conservative forces. That's why we are studying this. Potential energy is just valid for conservative forces. If you have non-conservative forces, potential energy is not valid. Okay, so it is valid only for conservative forces. While what are non-conservative forces then? If I say, let's say here I'm taking again, this is point A and this is point B. Now we move from A to B like this. This is our first work done, our first path traveled. Let's say second path traveled is like this. This is the second path traveled. Okay, and the third path traveled is like this. Now, the non-conservative forces are those forces which will depend on this. They'll be depending upon the path that has been traveled. It will affect it. If it will affect the whole work done throughout. Means I'll say the work done 1, work done 2, work done 3, they aren't equal. All the work done will be different because they are dissipative forces. They dissipate. In the sense, see, you take your palms, you rub them. In winters, why do we do this activity? Because our palm feel warm, right? Our palms feel warm. Reason is that friction force act, we know, we have seen this in laws of motion itself. Two objects getting rubbed together because of the intermolecular irregularities, there's a friction force present in the opposite direction of motion. But this friction force will go where? Okay, friction force is generated, but where it will go? It cannot vanish, it cannot be destroyed, it cannot be just eliminated, because it's, see, all the forces, it will just dissipate as a heat energy. So the frictional force is converted into the heat energy. That's why we feel the hands warm. So see, all these things that are dissipative in nature, they are non-conservative, like your viscous force. They always oppose the movement. See, if a ball is moving down and there is no friction, it will move very smoothly. But if there's air friction present in the calculations, there will be a resistance. Ball will take a lot of time and a greater time than the previous case in descending, because there is a resistive, there's a motion, there's an opposition to the flow. Since they have these opposition, that's why we say this, these are non-conservative forces. You take a ball, you drop it, ball will reach fast. You take it, you drop it in a bottle full of honey, it will take a lot of time to reach the final. In fact, it can just stick at one place also. So these are dissipative forces. Those are non-conservative forces. Here you cannot apply the concept of potential energy. Two bodies generating frictional force, they have potential energy? Straight away, no. Can they have a potential energy due to any other force present despite the frictional force present? Yes. Okay. Now, what is potential energy? That I'll tell you, because potential energy is a little more elaborative because of your forces, because this depends on force. So is this concept clear to both of you?
Yes, mom.
Yes.
Please write it.
10, mom.
Okay. See, coming to potential energy. So, see, in your lower class, especially in your ninth class, last you must have studied this. So, the concept of potential energy was there, and the definition said that it's the energy that is possessed by a body due to the change in the position, size, or configuration or orientation of the body. This is what the definition we usually study for the potential energy. This means that whenever the body's position is changing, the configuration means orientation, as in angle is changing, length is changing, size is increasing. You say a potential energy is there in your system. See, these definitions aren't incorrect, but they are incomplete because now you know the conservative forces. So you should know whenever there's a conservative interaction. See, when we say conservative interaction, this means interaction means forces getting exerted, force exerted. That is what is meant by interaction. While conservative means the conservative forces that we have studied, all the conservative forces. So energy due to conservative interaction means when the conservative forces are there. Like if I give you a small example, there is one mass, there is second mass. These two are the masses, and let's say they are separated by a distance r. So now between both of these, there will be a gravitational force that is exerted. If between these two, a gravitational force is able to exert, we'll say there will be a potential energy of the system. Potential energy will be there in your system. Reason is that conservative interaction is there. So potential energy will be present in your system. Okay, or if I give you one more example, let's say one charge is there q, another charge is there q, and both of these are separated by a distance of r. Now both of them will be able to exert electric forces, electrostatic forces on each other. So potential energy will be existing in this case also because it's a conservative force interaction exerting. So interaction basically means force. Are they able to exert force on each other or not? This is very important to understand in different systems, in different situations. You will see whether potential energy will be there or not. Because right now we will not do much of it, but when we'll come to the gravitation chapter, there you will have the gravitational potential energy. For that, this concept should be cleared in this chapter. From this chapter, you will get easy basic questions. This is from class 12th. But if I say two objects are there and they are getting rubbed on each other, this is one, this is two. And there's a friction force acting here between them. So this is, there won't be any potential energy because friction force isn't a conservative force. Okay, so only conservative forces. Work done against conservative force is stored in the form of potential energy, and if it's a non-conservative force, it dissipates as heat, like the friction force, viscous force. And potential energy gives you the whole concept of the conservative interaction. It is based on this. Also, one more thing. When we talk about the work done here, see, there is a work done by the, when we say no, work done is F dot S. So here there is work done by the internal force, and one is work done by the external force. Internal forces and the external force. This is a lot theoretical part. We'll come to numericals, don't worry. So see, internal forces are negative of the external forces, or you can say external forces are negative of internal. They are just opposite. But the potential energy will use the work done by the external force only. For this only you will use the potential energy. So what if the internal is given? Then if internal is given, you use this relationship and calculate the external. Okay. How your external will be given as negative of F internal. Now the way you had a work energy theorem, work energy is basically work kinetic energy. That entire full definition is work kinetic energy theorem. There is work potential energy theorem also. What is that? Let's say there is initial point A, here the potential energy is UA. There is a point B, here the potential energy is UB. So if I say change in the potential energy, it will be UB minus UA. And this change also gets stored in the form of the work done. This work done gets stored in the form of potential energy. This is the work done, while this is the potential energy. So work done gets stored in the form of the potential energy. Now, what is this work potential energy theorem? This can also be asked to you. This is potential energy difference is work done. This is the work done, but by the internal force in carrying a body from, work done by the external force, or negative of work done by the internal force, which I told you. Basically, this work done is the external work done. I told you here, there will be the external work done. So the same thing. Whatever is the work done by the external force, and if it's internal, you take the negative of internal. Basically, this is their relationship in carrying a body from initial to final position. Have you all got anything in today's class?
Yes,
Shanidhi,
ma'am.
Neha, you've got it?
Yeah. Yeah.
All right then. Okay, by looking at the notes only, let us just have a recap because a lot of theory part is there. Now I'll start with the gravitational potential energy. Not the gravitational, that we'll do in gravitation chapter also, but in this chapter, slight a bit. Neha, can you explain me by looking at the notes which you've written, this concept of conservative and non-conservative forces which we discussed?
Okay. So in conservative forces, we know that the forces are independent of the path. So, like if there are three paths given, so the work done in each path would be equal to each other. And in non-conservative forces, they're dependent on the path. So the work done in each three of those paths will not be equal to each other, like in friction. Okay.
Correct. Work done will not equal. Perfect. Basically, the work done is the same, and here the work done is not the same because of the path that is followed. Very good. So you've written it till here, no? Potential energy is left. Please start writing. Potential energy one, when Sanidhi joins, she will explain you what. Please write. Yes, Sanidhi, are you able to hear?
Yes, ma'am. Your video was getting stuck, so I just left the meeting and joined again.
All right. Neha just describe the conservative and non-conservative forces. So, Sanidhi, what did you understand by the whole potential energy part till now?
Just 1 second because your mic is going like high and low, high and low. So let me just bring my network 1 second.
It's okay, Sanidhi. You can read it from here also. Potential energy part, if you
Yes,
have trouble.
ma'am. Yes, ma'am. Ma'am, potential energy is the energy of the object, which it's of the system, because due to the body, what the body possesses, like the size, position, and like which direction it is in the field.
Okay. Then,
Okay, and so the examples are you have given on the screen: gravitation, potential, and
so
electric.
if the size is changing, position is changing, That will confirm that potential energy is there in the system.
Yes, ma'am.
There's nothing else to confirm. This is a definition of from your ninth classes NCERT, not from your 11th. In 11th, you have to check the forces. That's why I did the whole concept of conservative force and non-conservative force. If there is a force in your system which is a conservative force, then the potential energy will be there, not by just seeing the size or configuration or position. I already told you this is from your 9th class. This won't help in class 11th. You'll get such questions in gravitation where you'll not be able to identify the change in size, position, or shape. 3, 4 masses will be present. Interaction means the forces are occurring. That's why there's a conservative interaction here. Conservative means it depends on the initial and final point, not how the path has been traveled. So the whole concept of conservative interaction I tried to explain, because conservative interaction will only help you in class 11.
Okay.
So this definition won't be sufficient. If you please write down the notes, and if still there's a confusion, any of you, not just Sanidhi, please let me know. This is an important topic. Here, if you do it thoroughly, gravitation chapter will save your time. Okay, let's continue from here. See, gravitational potential energy's formula mgh. You must have studied it in your lower class. So that is just one very specific particular case of the gravitational potential energy. So here we are discussing, because this involves the concept of work done here for this derivation. That's why we are doing this. Other actual complete potential energies and gravitational potential energies, we'll be discussing it in the gravitation chapter. See, if a body has been taken from the surface of the earth to a point, so the force that is exerted is mg, the gravitational force. This is the gravitational force. And the displacement, let's say, to which it is raised is some height h. So work done, we know it is F into S, that is mg into h is the work done. Now, according to this theorem that we studied, work done is equal to the change in potential energy. So the change in potential energy is basically mgh. This is just one specific case that we studied. Okay, let's see a question, easy question based on this. There is always a reference zero of potential energy chosen. A reference line is chosen, which is the zero of the potential energy. Now, 3 points are there: A, B, and C. These are three separate questions. First question, the potential energy at the A point. See, the body has been taken from the zeroth of the potential energy to a particular value. That is, let's say 5 meter is taken. Okay, so when 5 meter, the height it is raised up to 5 meter, potential energy is written as mgh. Now the mass is 2, g is 10, height is 5, that is 100 joules. Okay. Second point, potential energy below. Now see, potential energy below means below your zeroth, the reference line. So that will be negative, because it's like you're taking a graph, or the number lines that we take. Basically, like the graph is the best thing. So UB will be equal to, still it is equal to mgh, that is 2 into 10 into 10, but this is minus 10. So energy is minus 200 joules. While the third one, potential energy at the C point will be 0, because there is no displacement produced. This, have you got this mgh?
Yeah, ma'am.
Oh, please write it.
Ma'am, once again, can you scroll to the top? Okay, ma'am. Okay. Done, mom. Done, mom.